Hello and welcome back to another episode in the Pint of Science live tour series. Today is episode 2, or I guess event number 2, depending how you take it. And today is day number 5 in Pint of Science, out of 14, if you're counting. So today we are doing another live tour. My name is Joanna. I'm going to be your host for today as we talk to a lovely scientist and have a cheeky tour of their lab. Now, we've asked all of our scientists during these sessions to pre-record their content so that we can look back, stop, and rewind as necessary to have a look through without disrupting the science that's going on. So throughout the live stream, you can join in on the conversation in the comments section to your right of the screen, or over to Twitter you can go to and type in the hashtag PintAU21 or PintAU21 and post your questions in there. Now, we'll leave the big questions for after the tour, but if you want us to stop the video or you've got a question about a certain thing that you see along the way, please put that directly into the comments as soon as you can so that I can stop the video in time or even be like, let's go back and have a look back. So, with that being said, you might notice me have a look around my screens. I've got a few camera situations going and I've got a whole I've got a whole group of lovely volunteers that are going to be helping me tonight. I've got Steph and Karen who are on the moderating. They will be looking for your comments and passing them along to me. And then I've got also off to my side here, my lovely video team who include Tom and Anthony. And so they'll be helping me out throughout the night, and I might just be referring to them slightly to get them to help us move through the content. So when we hold events at pubs around Australia, we ensure that we recognise the local Aboriginal and Torres Strait Islander nations, one of many that makes up the continent that we now call Australia. Now that we're holding this event online and our speakers and much of our audience are streaming from around Australia, we want to acknowledge all traditional custodians of country, the first innovators and scientists of this land. We pay our respects to Aboriginal and Torres Strait Islanders elders, past, present, and emerging, and recognise their continuing relationship with the land, waters and culture. We especially would like to pay our respects to the Jagera and Turrbal people as the traditional custodians of the land on which the Queensland Micro and Nanotechnology Centre at Griffith University is built on, our location for today. So, with that being said, I'm joined here today by our lovely tour guide for tonight, Dr. William G., who uses his chemistry expertise to investigate challenging forensic science problems. Oh, how very interesting. So, Will, would you be able to tell us a little bit about yourself and what we might be able to look forward to today during our tour?
Yes, so firstly, thank you for having me on. So my name is Dr. William G. I'm a senior lecturer at Griffith University here. My background is in chemistry and forensic science. So what I do in terms of teaching and research is I apply my chemistry knowledge to forensic problems. And today we're going to take a look through 2 of my labs, or 2 labs I share to be more accurate. The first lab is going to be a chemistry laboratory. So that's where we do a lot of our creating new chemical treatments for forensic type problems. So I do a lot of work to develop new fingerprint visualization treatments. And the second laboratory we're going to look at is more of an analytical laboratory. So that contains a number of microscopes, and it also contains some specialized forensic equipment like light sources and cameras and the types of things that I need to actually visualize the simulated evidence that we work on.
That's really, really cool. Now, well, just a few quick questions of my own to begin with. How many hours or what does your day usually look like when you are working within the lab? Are you there from like 6 a.m. to 6 p.m. or is it more like 12 to 1 p.m.? What's the situation?
So I tend to get in quite early because I'm more of a morning person. So I'm usually getting in between 6 and 7 in the morning, and that's before the emails get crazy and sort of the logistical stuff. So I try to do the hardcore grant writing, planning, teaching, preparation stuff in the morning. Throughout the day, probably about half of my day is either spent teaching, so either giving lectures, tutorials, maybe running a laboratory for undergraduate students. And I try to spend a couple of hours of the day in my research lab. But I've sort of gone beyond the point where I would be doing the research. So I'm generally mentoring honours students and hopefully PhD students as well.
Nice. Thank you so much for that context. So with that bit of information, I think it's now... Oh, actually, no, I do have one more question. How many people are usually in these labs, like on a good day?
On a good day, there's generally, well, COVID, space restriction rules have sort of changed a little bit, but generally 3 to 4 would be quite typical for the chemistry laboratory and slightly less for the analytical laboratory just because it's smaller. You'll notice that actually when I give you the tour, there is no one there because I actually did the recording on the weekend. So we do not make our postgraduate students come in and work on the weekends. So it will be very empty. But generally there's a handful of people typically working in most of the labs here.
Nice. All right, well, on that note, let's get started on the tour. Now, I do know that you are talking throughout some of these videos, so we'll just pay attention. And if you want us to stop at any points, or I might ask us to stop at some points, just so we have a bit more of a conversation about those things as well. So,
Sure.
Tom, can we get the first video up, please?
So my laboratory is quite typical of a chemistry laboratory. So a lot of the equipment that I have is quite typical of other types of chemists that work in research. So if you have a look around, you can see some equipment such as a rotary evaporator. This is what we use to basically remove solvents from some of the work that we're doing. To do research on fingerprints, basically what we need to do is we need to look at chemical reactions that occur in the presence of the materials that you transfer onto surfaces when you touch them. And that's mostly amino acids, and sometimes it's sort of fatty chain oils, which also are transferred. So what we typically are doing is we're looking at a whole bunch of different types of chemical reactions, and we're trying to find ones that produce some sort of change when they come into contact with the fingerprint.
So I have a quick question here, Will. So you've talked
Go
about
for
this
it.
chemical reaction process, but how long does one of these chemical reaction processes take? Is it over in like 5 minutes, or how much time do you have to dedicate to go through one process? And when you reach the end of that process, is that like tick, I've done it, I've cured cancer, or like where are we looking here?
So, well, there's a couple of ways of answering that question. In terms of actually the development process, so from like having an idea for a new technique for developing fingerprints up to the point of we've now refined and optimized it, it can be months, years. In terms of actually what police and forensic scientists actually want, they would prefer that if we come up with a new chemistry technique for visualizing fingerprints, that it's very fast. So they want to basically spray the reagent on whatever we're looking at, and then you get almost an instant sort of color change wherein the fingerprint kind of appears. So it's sort of this balancing process of what we want to do is have something that's very, very fast, but the actual development process is very, very slow. And probably one of the slowest parts of that is once we have found a new way of developing fingerprints, say on paper, which is what we're going to talk about a little bit, the next thing we have to actually do is compare it to the known techniques that the police already use, because they're going to want to know, is my technique better or not? So well, after we've done the hard work of actually developing a new technique, we then have to spend quite a bit of time actually doing sort of validation studies where we compare it to the known techniques and show how it sort of compares and contrasts.
Wow. I didn't realize there was so much involved, but I guess, yes, it probably does take a while to make sure that, we ensure that whatever we do as our process is a final thing that we can be like, yes, we know that this is the right way to do it, and what we're giving you is the correct answer, because, you don't want to lock the wrong person in jail. Have it look bad for everyone.
Yeah.
Hey?
Indeed.
Now, as we go back to the video, I'm going to start the video back in a second. Just a reminder for everyone else that if you do have any questions as we go through, feel free to throw them up in the chat as we go, and we can ask them as we go as well. So let's get back to the video.
Usually that's going to be a colour change. So we do a lot of research looking at different types of paper. And the idea is that fingerprints are invisible when they're left, but we can apply different types of chemicals to make them visible and then give us more detail in terms of looking at the fingerprint patterns that you can actually see. So my little workstation, I guess, is broken up into two main areas. We have this workstation where we do a lot of testing on actual fingerprint substrates. And if we come around here, this is our fume hood. So basically, if we're doing any sort of chemical synthesis or something that involves either toxic chemicals or using solvents that are bad to be sort of breathed in, we will do this inside of our fume hood. The point of the fume hood is that it actually has a negative pressure gradient. So basically, the air in the room is being sucked in out in this direction. So any chemical sort of fumes that are produced, they're going to be trapped inside of our fume hood and be sucked up and eliminated from the building that way, and we don't breathe them in. A lot of the research that I do is looking at creating dyes. Dyes are obviously coloured. They're the things that you find inside your clothing. If you make these coloured type things, your eye is very sensitive to seeing them. So I'm often, or at least my research group is often looking at different types of dyes as well as chemicals that produce light. So things like phosphorescence and fluorescence and chemiluminescence.
So just another quick question while we're here. So you're talking about dyes, but how many are we talking? Are you testing like 2 or 3 at the same time, or millions? What's the scale here?
So generally we're only looking at a handful of different compounds at a time. A lot of dyes, when you sort of break them down to their sort of chemical or atomic structure, they have very similar structures, and you just sort of subtly tweak them and then they change colour. So usually what we're doing is we're focusing on sort of a class of dyes, and we're hoping against hope that something that we secrete from our body can be used to either alter the dye to change its colour, or can actually be sort of chemically modified to turn itself into a dye. So they're sort of the two things we're kind of aiming for. At this point also, I will point out that I don't do all the work. My research group does most of the work in the lab. So if I take credit, no, it's mostly my research students doing all of this stuff.
And how many research students do you have currently?
So because I'm very new, I have a very small research group. So at the moment, I just have one honours student, and because I've come from the UK.
Oh no, I think we've lost him.
Dropped out. Oh, I'm back. Did I drop out there?
You dropped out for a second there. You were just mentioning that you've just came from the UK and you have one honours student. And that's
yep,
about
I have a PhD student also overseas. So yeah, my group is very small compared to some of the research groups around.
Wow. Okay. We'll have to keep that in mind. So this is all. So is this your honours student that's also holding the camera for you?
No. I requisitioned my girlfriend to help me film this because it was on the weekend. So I didn't feel bad about asking her to help. But we will see my honours student in a second. So I did do some of the filming during the week. So she will appear in a second.
Oh, excellent. Well, I look forward to seeing her. So I think let's keep going with the video.
Basically, anything your eye is good at detecting, this is what we're sort of working on at the moment. Grab this. So if we take a look around, we can see some examples of the types of work that my research group is doing. So in each of these cases, we can see a lot of these substrates are on paper. What we've done is we've placed a fingerprint on the paper, and then we've applied a lot of these different types of either dyes or chemical reactions that produce dyes, and that gives us basically colour wherever it was touched.
Hold on. Hang on. So whose fingerprints are you using? Are you just using your own? Or is it like, do you have to use like a
generally, if I'm showing them in public, it's generally my own fingerprints because there's some issues to do with privacy and biometrics and ethics and these types of things. So generally they're going to be my fingerprints if you see them. But when my research group is doing research, what we need to do is we need to have a larger sample size to make sure that what works for one person will actually work for a larger sort of population. Because we're doing sort of fundamental research, we don't use particularly large sample sizes. So generally we'll use 3 to 5 people, and we'll probably harvest anything from 20 to 50 fingerprints from those people so that we get fairly decent sample sizes that we can test our methods properly.
Wow. And so do you just go around requisitioning honours students and like PhD students to do this? Or do you have like
we do ask them first, and we do have ethics forms that we make them fill out so that they're aware that, you know, they're giving up their biometric information for the cause. But yeah, we do that. I like asking forensics lecturers and forensic undergraduate students and postgraduate students just because they're aware of sort of the issues and the importance of this sort of stuff.
Ah, okay. And I know that with people's fingerprints, they can have like different designs, and when you're trying to identify them, you know, I think there were whirls and something that people call them. Awesome. And does that also have to go into play when you're trying to identify if a dye is going to work? Do you have to be like, excuse me, what type of fingerprints do you have? Or do you have a whirl for me? I need to test a whirl.
No, we don't really care so much in terms of actually the details of the fingerprint themselves. What we're generally looking out for is, especially during these COVID times, we have to make sure that people haven't washed their hands within, say, the last hour, because that depletes the materials that you'll leave. We also try to avoid people that have handled food or have contaminants on their hands if we can. Honestly, they're the main ones. We don't want really, really clean fingers, and we don't want really, really dirty fingers. We just want generic fingers.
Right, okay. So if I've had a packet of chips, I'm out. At least for the next little bit until I clean my hands.
Yeah, well, if you've had a packet of chips, it'll probably work considerably better, which is one of the things we want to, because you'll have lots of oils on your hands. So part of it is not giving the false impression that our work is better than it actually is through actually having some of these things on your fingers.
Oh, it sounds like a very, very challenging balancing game. All right, let's keep on going. There's so much to
basically
see.
Colour wherever it was touched. What the aim of what we're doing is basically trying to get better information from the fingerprints that police can then use to identify essentially the people that touched whatever the surface is. Because the police rarely have access to perfect fingerprints, they're often dealing with smudged fingerprints or fingerprints that have been overlaid on one another. Basically, the more information and the clearer the information actually is, the more likely it is that they can link it to the person that touched that substrate. So if we have a look up here, we can see a whole different bunch of chemicals. So these are the ones that we would use often in making up our different chemical formulations. Because we deal with a lot of forensic science, or basically forensic scientists, and they're not necessarily trained as chemists, a lot of our starting materials, so these chemicals that you can see, are either safe, non-toxic. Basically, they're things that you can use outside of a chemistry laboratory. So it's not really helpful to create a brand new treatment for forensic science if it's going to be horrendously toxic and it'll poison whoever tries to use it. So one of the main aims of our research group is to use chemicals that are relatively benign.
So with that, actually, sorry, I should have given you a warning. My bad, team. Now that's made me forget my question. Oh, sad. What was it going to be about? Oh yeah, so with all these chemicals and stuff, I know that a lot of biological labs, the cost for reagents and all the chemicals can get quite expensive. Does that mean that if you're working with everyday chemicals, so to speak, or friendlier chemicals, does that mean your cost is a bit cheaper, or do you still have the same similar running cost to a in theory, stereotypical lab?
No, I run my lab on a shoestring budget, which is actually, good because another consideration, I guess, for the research is if you can use very cheap, common chemicals, it means the applicability of the research is wider. So it's not just, first world countries that can afford to pay hundreds of dollars to generate their fingerprint reagents. It will actually be used in, countries that are poorer, and they can, then the impact of sort of your research is wider around the world. So it's something that I try to do. It's if you can, one, be good for the environment, and two, be low cost, it just increases the popularity if you come up with something good. Like, people will naturally want to use your method if you can have those two things.
That sounds really, really cool, and I think a very, very common message that we're hearing coming out of everywhere is everyone being sustainable and thinking about more than just getting the answer right. It's how can we be strategic and get the answer right. So that's really, really cool to hear. And sorry, go.
Yeah. Actually, on that, one of the main projects that we're looking at in my group at the moment is they have these fantastic, optimized fingerprint treatments that give amazing results, but the main liquid component that they use is a CFC, so something that depletes the ozone layer. And the reason they do that is because it evaporates incredibly quickly, and it's incredibly safe from breathing it in and sort of, a toxicity sort of application. But it's such an environmentally poor chemical that the chemical manufacturers have banned it. So a lot of the forensic treatments that use that now are, we've got stockpiles for a little while, but we definitely need a replacement soon because we just can't make it anymore.
Oh, I didn't even realise that would be an issue, but there you go. I guess that makes sense. Similar to other science fields, I believe, they have the same challenges of if they're using liquid helium or something, it's becoming a more and more expensive, but also limited supply.
Yep.
Interesting. Very, very interesting. And actually, talking about overseas, I do have a question from the audience. They want to know, how does it work with you having an overseas PhD student? How do you interact? How do you support them? And how does that relationship work?
Not as well as it perhaps could have.
Is this a relic of
when I left
COVID, or?
It was not. So the fact that I'm in Australia at the moment is because I guess I timed it in such a way that I managed to arrive in Australia before, I guess, all the borders kind of locked down. So the way that it had to go is that my PhD student was about halfway through her PhD. So the first thing we had to do was set up a new supervisory sort of arrangement for her. So usually you would have at least two supervisors. So you would have a primary supervisor and a secondary supervisor. So what we did is we swapped roles. So I'm no longer the primary supervisor, I'm the secondary supervisor. And there is also an additional supervisor added on. So she now has 3 supervisors, whereas she would normally have 2. So I'm kind of the overseas one. But yeah, it's hard with time zones, for instance. Everyone's getting very good at communicating through things like Skype and, what we're doing right now and these types of things. So it's not insurmountable, but it's certainly not ideal.
Right. Okay. Well, I'll make notes, and I'm sure any of our people out in the audience who are looking to become PhD students or starting to go into research, keep that in mind.
It is definitely more ideal to have your supervisor in your own country. I can say that is 100%. Don't have a boss in another country.
Or even in the same time zone is probably going to help as well, hey?
Yeah.
Okay. Sorry, I keep getting distracted from this tour. We better get back to it. Let's see what else is going on.
So travelling around here, we can see some things that are quite typical for a chemistry laboratory. So these are both chemical balances. Basically, one of the things we really need to do is to accurately measure out the reagents that we're going to be using in our fingerprint treatments. That's for 2 reasons. Firstly, the ratio of the reagents that we use is quite important for getting the appropriate sort of coloured materials that we want at the end. So we need to be very, very sure that we've weighed out the correct amounts when we do it. It's a little bit like cooking. The other reason is for reproducibility. So we need to make sure that if we discover something new, that we can report it to forensic scientists and tell them exactly how we went about making it. If we have a look in the middle, we can see a couple of types of creams. One of the problems we actually have when we're doing this type of research to develop a whole bunch of different fingerprints is that we quickly sort of use up all of the residues that exist on our fingers. So one of the ways around this is to actually apply different types of creams to our fingers. Some of those are using the actual chemicals that are placed or that our body creates themselves, like squalene, but a really fast way to do it is to basically apply something like sunscreen, because that contains a lot of the same sort of oils that we might target when we are developing a new chemical treatment. So it means that when we optimize, we can actually optimize for something that we can produce quite a lot of prints using. And once we've done that, we can then switch back to just our own fingerprints when we, validate that it actually works in the real world. So here on the end, we can see a tripod. It's currently missing its camera, but this is usually where we do some of our documentation. So one of the most important things that we need to show when we're doing our research is that we can actually develop fingerprints well and show that to police and forensic scientists. So one thing we're doing is we're typically going to be here's some examples that we prepared earlier, but we'll be photographing these and then showing the photographs of how they actually look afterwards. This is basically what the police and forensic scientists are going to be interested in seeing. And that really gives them a good indication of how well our techniques are going to, scale up against some of the ones that they're already using. So
Hang on. Why is there a back off sign? Really important, I know.
Yeah, I kind of figured this question was coming. It's not my lab. I occupy maybe 50% to a third of the lab. So there is a little bit of territorial nature amongst researchers in terms of guarding space and chemicals and these sorts of things. I didn't put that there. That's a relic of the person who had the space before me, but I also didn't remove it when I saw it. So, yeah. Got to guard your own kingdom.
Fair call. And I see that all of your chemicals had your last name on them as well. So,
yep.
Got to keep those locked onto the key pretty
Very
much, right?
easy to identify them.
Now, I don't know if you'll be talking about it a bit later, but I saw just off to the left of the video, there was a machine. Now, Will, do you talk about that a bit later, or...
Sorry, I dropped out again. What was that?
Oh, okay. Hello.
Hi.
Oh, no. The machine that's just off to the left of the back off sign, I don't know if you go into more detail a bit later, but I'm really curious to know what it is and how does it work?
Right, so I don't. That's called a rotary evaporator, and basically what that does is if you have a flask or something that contains a liquid component and you don't really want the liquid, that will apply heating. So if you see there's a bowl in the bottom, that's sort of basically you can heat up the water in that and heat up the flask, which makes it faster to evaporate off any liquid that's in there. In the top, there is a condenser. So that is sort of water cooling at the top. So what happens is you heat up your flask, any liquid enters the gas phase, and then it'll travel up, hit the condenser and be sort of separated away from the initial flask. If you've ever been to a whiskey distillery, that's basically a whiskey distillery but miniaturized down. So if you see the way that they sort of, separate the alcohol from water mixtures in a distillery, that is a small laboratory scale version of that allows us to get rid of liquids.
So are you saying that if in an apocalyptic situation and you had no other choice, you could be the whiskey maker?
You could distill alcohol using that device, yes.
Right. And you'll be the expert on that. Excellent. Okay, we'll keep going.
I would not use that one because that one's kind of dirty, but yes, you could use that.
Alrighty, okay, I'll stop giving ideas to our audience members. Alrighty, let's keep going with the video and see what else is on.
So that's basically my chemistry laboratory sort of in a nutshell. Next we'll go and we'll have a look at the development laboratory, which contains a dark room, and it's where we can use some forensic equipment to really showcase what our techniques can actually do. So this is Kristen, my honours student. She's going to go through and show us how she does some of her fingerprint research. Starting with cutting the paper. So we do a lot of forensic research on developing fingerprints on porous substances like paper. What are you doing now, Kristen?
I'm grooming the fingerprints, so I'm putting extra oil on them so they look really nice.
Excellent.
What's that word she used? Did you say she's grooming her fingerprint?
Yeah, so she's adding additional material onto her fingers, and in the terms of fingerprint research, we call that grooming a fingerprint.
Because, like, is it similar to, like, grooming an animal that, like, you're needing to clean, but instead of clean, preparing it or brushing your hair equivalent?
Kind of, I guess. I've never questioned that. It could be.
Okay, cool. Okay, so she's grooming her fingerprint, and she's only got half the glove on. Is that because she needs her other fingers to do the for lack of a better word, the sciencing?
So basically what we want one fingerprint only when we lay fingerprints. So what she's done is she's removed her glove on basically one finger, placed it down, and because she's wearing gloves over the rest, she can handle the paper without transferring any of her other fingerprints onto it.
And then I'm sure you've probably also done this work, and I should probably be asking your honours student this. How many times do you end up accidentally printing things with the thumb now that it's exposed?
Well, I think we'll see that she'll very quickly put her gloves back on, but something that you learn fast when you're doing this sort of research is you have to be very good with your personal protective gear. It's not even when you're in the lab. So a lot of the paper we use is commercial paper. And when we receive it from the store, we're obviously not wearing gloves there. So it's all the way up to the point that you actually use it. You have to kind of try to prevent yourself from touching anything because you will find it later on.
There you go. Alrighty, well, let's keep going and see what she gets up to.
So fingerprints can be developed using either amino acids or oils, and we are looking at oils in this case. Safety first, so gloves are on. If you look over here, we have some iodine vapor. So this is one of the means that's sort of known to develop fingerprints. You can see that orangey yellow colour. We're spraying our reagent, which sets the iodine. Hopefully gives us a nice, clear, focus, fingerprint.
That's how
Looking
quick
good?
it takes.
Yep.
And that's what all the people doing the forensic stuff, that's all they're doing? Or is there like more steps to this and we're about to go to more steps?
For this treatment that we're looking at, which is not one that the police would typically use, we're trying to make it better than what it is. It's very, very fast. The downside to this treatment is it typically only works for quite fresh fingerprints. So if you've touched something within, say, 3 days, it can develop a fingerprint usually. But if it's something that was touched a week ago, 2 weeks ago, a month ago, it will give you nothing. So generally, forensic people, they want their treatments to be sort of done within maybe an hour, I guess. You need to be able to, start to finish full development. Most will be done in that sort of time frame. So this one is pretty fast.
There you go. Wow, I never realized how quick it was. I feel like this is like using those magic pens back in the day where you'd write in lemon juice and then spray it. Oh, this is cool. Yep. Alrighty, let's keep going. Let's see what else we get up
Fingerprint.
to.
Looking good.
So this is our temporary fingerprint documenting sort of station. Don't forget the light source. Whoop. Look at that. Lovely.
All right, this time we're going to be looking at cardboard instead of paper, which is a little bit more difficult to get fingerprints from.
So, hang on, why is it so harder with cardboard?
Yeah, that's a good question. So the type of evidence that we're looking at the moment, paper, is classed as an absorbent surface. So when you touch paper, it will actually sort of sponge chemicals off your hand when you touch it. The degree of sponginess of the surface will dictate how good the technique actually is. And paper is quite good at absorbing chemicals, whereas cardboard's it's got a rougher, sort of more solid surface, and it's not as good as actually absorbing the chemicals off your fingers, which is why it's more of a challenging surface than, say, paper. It's also darker, like paper's white, which is really, really easy to see coloured things on it, whereas the darker the surface gets towards black, you run into more challenges and problems with that too.
So does that mean there's also researchers out there looking into techniques for printing on dark materials or printing on a more challenging surface than paper?
Yep. So for, say, a black surface, you wouldn't be able to use the first technique. You wouldn't be able to see it, but you could use something that generates fluorescence. So basically when you shine light on it, it shines light back at you. There's lots of fluorescent fingerprint powders, and there are some chemical fluorescent techniques as well. So you couldn't go for dye development, but you could go for something fluorescent.
Right, so does that mean in a police's kit they might have several methods of identification so that, I see, okay.
Yep,
okay.
So there's about, in terms of chemical techniques, I think there's about maybe 15 to 20 really good techniques for there's so many different types of evidence that you could come across that you need sort of a wide gamut of techniques for the right situation.
So, okay, on that topic, Joe wants to know from the audience, what surfaces are the easiest or hardest to test for fingerprints? So we've talked about paper, but what about a more open, not that we're trying to elude the police, but what's the situation?
So absolutely the best surface is something that's very, very smooth, flat and solid. So if you think about, say, glass, like if you touched a window, that is one of the best surfaces that you could recover a fingerprint from. You wouldn't need to do any of the chemical techniques that we use. All you would need is just the right coloured fingerprint powder, and you would apply that with a brush. And I'm actually really bad at using fingerprint powders and brushes. Like I'm not delicate enough when I do it, and I tend to destroy the fingerprint. But the police are very well trained to actually do that. So that's a non-porous or something that doesn't absorb chemicals, and something that's very, very flat or smooth is very easy to treat.
Okay, and what about the other end? What's a surface that scientists currently are trying to figure out how better to fingerprint on?
Okay, so the worst case scenario would probably be a rough surface that is got a complicated pattern on it. So what I usually use is a Skittles packet, which is not rough, but it does have like that rainbow pattern on it, which is quite challenging to get a decent colour off that. What else? So anything that has a pattern that's similar to a fingerprint is very hard. So obviously you're looking for a fingerprint pattern, but if it happens to have like a swirly pattern on it that sort of looks kind of similar to a fingerprint, that's really hard. Those are the main challenging sort of surfaces.
So I should put my fingerprints on a page filled with fingerprints, and then that way you won't be able to tell it's my fingerprints or if it's the picture underneath it, in theory.
So if you lay a fingerprint on top of another fingerprint, that's really, really hard. Probably couldn't be done without some sort of weird high-tech computer separating program that I very much doubt is common in the forensic community.
There you go. I didn't realise that it also mattered what was underneath it or looking upwards, not just the surface that it's on. Huh. Well, there you go. Alrighty. Well, let's keep going and see how we go with fingerprinting on cardboard.
As before.
into the fume hood. So again, we're using iodine to fume, get iodine inside the fingerprint, which we can use to develop the colour.
Wanted to see it.
We're going to be using a gel this time. Oh, it's shiny. There we go. You can see some development of the fingerprint in there. So the iodine is reacting with our reagent and going a nice dark colour. So in the last laboratory, that was basically where we do a lot of our chemical type synthesis. So that laboratory was safe to handle dangerous chemicals, to create new types of chemical treatments, and essentially be exposed to chemical hazards safely. This laboratory, which you can sort of see around here, this is one of our more analytical-based laboratories, and it's where we house a lot of...
So before we go on to your analytical lab, we have been receiving a few questions coming in from the audience in regards to what we've just been watching. And I want to address them with you now before we go any further, just so it's still all fresh in our minds and in case we have to go back at all. So,
go for it.
One of the questions I have is, back before you mentioned how you're not very good with doing the dusting type because you kept destroying the fingerprints. How can you develop fingerprints without destroying DNA evidence is a question that has been asked from the audience.
Yeah, and that's a really actually challenging area in forensics and in fingerprint research as well, because often when we apply chemical treatments, it's great for seeing the fingerprint, but it degrades any DNA that happens to be there. So it's sort of a chicken and egg problem. You can't actually harvest any DNA that's been transferred if you don't know where the fingerprint is. But unless you apply the chemical treatments, you won't know where the fingerprint is. One aspect of the research we do is, so I work with people who are experts in DNA recovery. So whenever we have a new treatment, basically I pass some of our evidence that we've treated along to them, and they will see whether or not they can actually recover DNA from it. One of the challenges is if you apply metals to the fingerprint, because that can sort of catalyse breakdown of DNA. It can also interfere with DNA amplification, which is one of the things, because you're working with really tiny amounts of DNA if it's just touching, so you need to actually make more of it. And if you apply different metals as part of the fingerprint development technique, you sort of prevent this amplification process. Really, that's a problem for the biologists. I tend to not worry about that too much, but it is a real consideration. It's something that we need to sort of test for. If our techniques prevent DNA analysis, it's not the end of the world and it still may be useful, but in a perfect world, you would want to be able to find the fingerprint, then harvest DNA from it. If you know where the fingerprint is to begin with, so for instance, a fingerprint actually just on a window, you can probably just see that without me doing anything for it. So then in that case, you can sometimes just get a swab some of it for DNA and then treat it for the fingerprint.
Oh, so when people collect the swab, and now this might be going outside your territory, please let me know if it is. So when they go to take the swab, don't they also destroy the fingerprint, or is there a way to collect?
Yes, they do. So it's a case of you want to maximise evidence recovery. And if that means you lose, say, 1/4 of the fingerprint detail, but you gain DNA evidence, that might be a worthwhile trade-off.
Right.
Sometimes, if you're lucky, you can literally just photograph the fingerprint before you've done anything to it, if it's like on a window, and then do the DNA and then try to amplify the fingerprint later on, and you sort of get the best of everything. But yeah.
Huh.
If you're lucky, maybe there's a terrible fingerprint that you can't use, which you then use for DNA analysis, and then you go for the good fingerprint, which is elsewhere.
Right. Okay, that makes sense. So we have a question from the audience. Azuzina asks, in a crime scene, would you apply the chemicals directly on the surface, or do you collect the fingerprint in some way, like copying it onto paper first? Or like, for example, I've seen in crime scene shows, because I watch too much CSI, there's like this tape thing that they use to collect it, and they're like, collect a sample. What's the real situation?
It depends, is the answer to that. If it's something that you can take away to a police laboratory or a forensic laboratory, you would probably do that, simply because the light sources and the techniques you have available in a laboratory are wider than the ones you would have at the crime scene. So if you could take an object, go down there, that's probably what you would do. So you talked about tape lifting. That is something that is done. It's used for, I think, fingerprint powders more so than chemical techniques. So if you can, that's for smooth sort of surfaces. If it's something like a doorknob or something, you would probably apply a powder. You would photograph it, because you always photograph all the steps that you do. And then once you have the photograph, you would do a tape lift and take that away as evidence that you would keep. Final sort of scenario is, let's say you are in a room that had wallpaper. You can't really take the wallpaper away with you if someone's touched it. So you would have to apply the chemicals to the wall, and then you would photograph that evidence there, and it has to stay, because you can't knock down the wall and take it with you.
Okay. All right. I think, wow, this is leaving me with so much information in regards to forensic stuff going on and things that I hadn't considered.
It's complicated, right?
Yeah, there's a lot going on, and I guess there is a lot that like individual researchers are doing within the field. So I think we should probably get going with a few more of the footage, because there's about 10 more minutes left on the footage, and then we'll come back to some more of these questions, because I think that there are a lot of questions coming through, and I want to make sure that we make time for it, but I also want to make sure we see all the video footage that you prepared. So let's have a look at the rest of the video.
Forensic equipment. So one thing we actually need to do is we need to validate all of our new forensic techniques using the same types of equipment that police and crime scene examiners would use in the field. So a lot of that equipment we have stored here at Griffith. This is my bag of fingerprinting type materials. So one thing that we have is a whole selection of different types of fingerprint brushes, different types of fluorescent fingerprint powders, some of the newer infrared powders that you can visualize or see using full spectrum cameras. So those are cameras that you can take photographs in the infrared or in the ultraviolet. The point of having a lot of these currently used forensic fingerprint powders is that if we create something new here at Griffith, we need to be able to show how well it compares to the currently used powders. So what we hope is that we create new techniques that work better than the currently used techniques, but the only way that we can actually prove that is by running our experiments and then running similar experiments using the equipment used by police and forensics here in Australia. So I have a lot of different types of chemical development methods that are used by the police. So one is the powders, as I showed here. We also have some of the purely chemical development techniques, so things like anhydrine, DFO, indane-dione. These are the chemical transformations that are used by the police to sort of visualise fingerprints. In a second, I'm going to show you the forensic light sources that we have in our darkroom. So basically, these are very intense light sources that allow you to see fluorescence from things like these fluorescent fingerprint powders shown here. So also in this laboratory, you can see over here, we have a fairly wide selection of quite advanced microscopes. So given that a lot of evidence is sort of microscopic in size and detail, so if you think about a fingerprint, the actual details in the fingerprint are quite small. We use a lot of microscopy to then see these details clearly. A lot of these microscopes are very advanced, so it's not just being able to see very, very small items or types of evidence. We can also do additional types of analyses using these microscopes. So we can do things like infrared analysis or even different types of chemical analysis actually using these microscopes. And that can tell us what might be present on a person's skin when they touch the surface, or we can measure different types of fluorescence very, very accurately. This just gives us a lot more information that we can use to either develop new techniques or
even improve currently existing forensic techniques using new types of equipment. So in a second, we're going to go into the dark room, so you won't see me anymore. We'll just have a look at some of the equipment that we use. But this is the other laboratory that I spend a lot of my time in. So chemical laboratory as well as this analytical laboratory. So this cramped space is the dark room that I have access here at Griffith University. So we see it has a sink, but it also importantly has the different types of forensic light sources that we make use of for our research. So just going around, here in the corner we can see we have a couple of different types of materials and surfaces. So we've got some ceramic plates, we've got CDs, we've got glass,
fingerprints.
but we need to assess many different types of material and surface when we're doing our fingerprint type research, just to show it's applicable to different types of material. Here we can actually see an iron, so if you do ironing you'll probably recognise this type of thing. The reason we've got one in our forensic laboratory is because many chemical techniques for fingerprinting actually rely on providing heat and moisture, so that drives our chemical reactions forward. And you can buy very, very expensive equipment that sort of, acts as our chemical reactors, but you can also just use like homemade irons, which costs a fraction of what you would pay for the bespoke systems. This is our first light source, so if we have a look here, this is, basically I call it a lightsaber, though for obvious reasons, but this is actually the type of light source that a forensic practitioner would use when they're going to a crime scene. So spin it around, find the button. So basically, very, very intense sort of light. So obviously I've got the blue setting. We can crank that right up. And basically this is what will be used to go around a crime scene and attempt to identify different types of evidence. So that's sort of portable, that's what your crime scene examiner would take to the scene, but there's also this one which is orders of magnitude more powerful than the handheld one, and this would be found usually in a forensic laboratory. So depending on whether or not you're going to be collecting evidence at the scene, you would either use this one here. If you take that evidence back to a forensic laboratory where you've got perhaps more tools and more instruments that can help you, you would probably use this powerful one here. Now I've got it set up and pointed at a $20 note. We'll turn the lights off for a second and show you what it can do. Hit that button. Right, so if we have a look, this is currently applying ultraviolet radiation, and as we can see, it's a $20 note, it's got the big 20 above it, but we can see underneath that it has fluorescent features, so a second 20 appears, as well as the serial number across the bottom. We'll just dial it down a little bit and see if we can... That sort of highlights, we can just see those security features coming up, and they're present mainly to stop forgeries. So it's actually quite hard to forge money. What they do is they incorporate many of these different kinds of, challenging features to replicate. And these types of fluorescent features are one such security feature as well. Obviously, we're more interested, in fingerprinting here.
Before we go on to fingerprints, now I've realised you might actually cover this. Joe from the audience wants to know, when it comes to developing fingerprinting techniques for money, is there anything considerations you have to put into place, or is that what we're just about to talk about?
No, and yes, there is. So money is one of the hardest substrates actually to try and get fingerprints from. You've got the initial problem of most money has been handled by many different people over the course of its life. So actually getting a nice fingerprint from money is inherently kind of hard. Also, as a substance, the money is kind of made out of a weird plasticky type stuff, which is probably some sort of huge trade secret as to what it actually is. Couldn't tell you what it's made from. And it's also coated in sort of like nearly, not a solvent, but something that makes it a little bit slippery when you handle it, just probably so it goes through the ATMs easily. And because it's got this chemical film on it, it interferes with a lot of the chemical treatments that we actually have. So the best way, I think, to get fingerprints off money is to try for using powder and not chemical, but it really needs to have been touched relatively recently and not by lots of people if you want to get success from it. So yeah, money is hard.
So it looks like we can only print money that comes from people's wallets, really, hey? That would be...
Pretty much. Like American money is different because American money is made of paper. So the research we were talking about before would be probably more applicable to it. But yeah, our polymer money, really hard.
They've tried very, very hard with polymer money, especially like, with all of this stuff to make sure we don't do any money laundering. It's so cool. And I didn't realize there was, I knew there was something going on, but I never knew or have seen that UV bits. That's so cool to see. It'd be interesting.
So when you actually go through an airport and you hand over your passport and they look at it, one of the things they have underneath the counter is a UV light like that, and a passport has the same features in it. So they will be looking for the same sort of fluorescent things popping up to make sure that your passport is a real passport.
There you go. And so with the new money that's coming out, because we're getting this rollout of the new banknotes, do they have anything else just as quirky, or is it like a little bit different, or do you know?
Yes, they do, but they're top secret. So they don't actually want people to know what the security features are within them. Some of them, for older money, you can just look them up. But I did my PhD with a friend who then got a job in the Mint, so the Australian Mint, who basically went through and developed a lot of these types of things. And she's never told me what's actually in it because she's not allowed. But yeah, there are more than one security feature. There's generally like redundancy of many different types of security features in it.
Fair enough. All right, we better keep going. We're running out of time. Oh no.
Here's a good example of fluorescent type treatments. So these are glowing in the ultraviolet light. Get a little bit closer. You can start to really see nice clear details using these light sources. So these are the types of materials and equipment that are used by forensic practitioners, and we use them here at Griffith to replicate what they can actually do. Very important for our research to show how it actually functions under the conditions that they would use themselves. So this is one of our experimental materials that we've made in our chemistry laboratory, and it's something that we're trying to process in the form of a fingerprint powder, but we haven't quite succeeded just yet. So what's interesting about it is if we turn on our light source, firstly it's very fluorescent, which is something that we quite like. I'll turn off the lights in the darkroom. I'm going to crank up the intensity quite a bit. So, like so. Not much change evident on this. But the really interesting thing about this type of material is that once you turn off the light source, you can have sort of a long afterglow, which you can then use to potentially photograph and get really good images without any background interference from the light. Because if we have a look around, we can see all of this background fluorescent stuff on the surface, so sort of beneath the vial. But I'm going to turn the light off and we'll see what happens. So there you can see there's that sort of slow decay of light, which gives you a couple of seconds to photograph it using your camera. So basically we're hoping that this is going to be a way to take really good images of fingerprints without having any sort of background light interference.
Well, that is very, very interesting. Now, quick question about that. Does that mean that over time, as we develop this technology more and more, we want to be looking at increasing that decay time so there's more time to take photos, or?
Yep, definitely.
Okay.
The problem with that material and the way it hasn't worked is once you take it out of its vial, it works for maybe an hour, but the light that you get back starts to decay as the material breaks down. So what we need is a more stable material that will keep working over days, months, years. That one has no storage sort of ability with it. But you're right, what we really need is something that lasts for probably 30 seconds would be optimal. So something where you have time to sort of fiddle around with your camera, take a photograph, and yeah. Problem is, the longer you wait, the amount of light will get less and less and less. So it's quite hard to have a really long-lived and bright material. Usually it will either be bright and decay quickly, or it will be relatively faint but last a long time. So finding the optimal material is what we're trying to do.
Oh, and then once we find the optimal one, we'll find out about something else that'll be just as optimal. Oh, yep. Gosh, it just keeps on going, doesn't it?
Yeah, research never ends.
And neither does innovation. It's so good. We keep getting better and better at things. Now, Beck Watts from the audience wants to know, are you currently working on any hypotheses yourself, or are you more of a teacher nowadays?
Good question. In terms of the breakup of my time, 40% of my time is doing pure research, so, coming up with my own thing. 40% of my time is teaching, and 20% is other, which could be anything, really. Fulfilling roles within the university that they require of me. So nominally, it's about 50% of my time is doing pure research, where I just come up with random stuff and test it. And the other 50% of my time is teaching the undergraduates, teaching the postgraduates, doing all that sort of stuff.
Oh, there you go. And would you call that kind of breakup very similar for someone in your position, or like a very stereotypical across academia?
That's an interesting question. There is probably 3 types of academic roles that are quite common. There is the teaching only role that has like 90% of their time teaching, 10% other. There's the research only role, which has 90% research, 10% other, which could be teaching. And then there's the balanced role, which is what I'm on, which generally has about 40, 20. So it really depends. Like, the university will sometimes go out of their way to hire researchers, in which case they will get the research intensive people. Sometimes they'll be developing a new taught course, in which case they'll go for the teaching intensive people, or they may have a pretty good blend of everything, so they'll go for someone who has sort of a blended profile like me.
There you go. Now, I am aware that we are running a little bit over time, but I do want to ask you, I think I will have to make this the last question, and maybe afterwards, Will, if you're comfortable, you can hop on and answer some questions live on Twitter as you feel comfortable to do. So my last question for the night is probably a little bit off topic, but also probably it is on topic, actually, in hindsight. The question is, as a forensic scientist, do you have to testify in court on behalf of the police as an expert witness? If you're allowed to comment on that.
No, I do not, because what I would always use for my research is simulated evidence. So because all of the methods that I use are untested, they would never actually use real evidence from real cases using my methods. The way it works is I do the research, I publish it, and then often the next step after that would be that a police laboratory would look at my research and go, oh, maybe that might be useful. And then they would do a sort of a study involving their types of evidence, but it still wouldn't be real evidence. And then if they were convinced by that study, way down the line, they might start to incorporate it into actual sort of casework. I'm happy about that, because I think the idea of testifying would be really stressful. But it also does sort of highlight an aspect of my research that, because I sort of live in academia, one of the important things I do have to do is go and form relationships with actual police officers and forensic scientists so that they can tell me what the problems actually are. Because if I didn't do that, I would never have sort of an idea whether I was working on something that was relevant. So one of the things I've done here since starting is to establish quite a good relationship with Queensland Police. And every couple of months or so, we would invite them to Griffith. They would come and they would talk about some of the problems that they're having in their forensic sort of casework. They might talk about a type of evidence that they collected that they just couldn't process. They had nothing sort of good for that. And I would then start looking at that as a project. So the police don't necessarily have the best sort of research capabilities, and I don't necessarily have the best idea of the types of research that they want. So it's only through sort of collaborating together that we can actually sort of deliver the best outcomes for everyone.
And I think that applies to a lot of fields of science too, doesn't it? Where there is this interplay between both scientists and the researchers going through to the industry of actually putting into force what's going on, and that relationship needs to keep on sustaining, or otherwise, what do scientists know what needs to be researched besides being like, that's a really great idea, I want to do that. So I think that you pose such an interesting thing, that it's so lovely that you get to work with so closely with the Queensland government to be able to make sure that what you're doing actually meets the audience, and that when you do,
it's also it makes sure that they're also doing what they need to be doing in terms of processing crime and solving those sorts of cases. Like, we want them doing that. We don't need them sort of playing around in the lab like I do.
And do you get a lot of police officers coming up to you and being like, we're having a lot of trouble with, fingerprinting this. Could you have a look at solving this? Or do you know someone who could look into this for us? Do police officers ever say that to you?
So typically I have sort of a liaison at the university who is a police liaison. So it's his job to basically be the intermediary between me and whatever police happen to have problems that they want looked at. So that's literally someone's job, is that. I have the relationships that I've sort of established in the Fingerprinting Bureau in Queensland. So I know those people pretty well. And the only other sort of area where I'd come into contact with a lot of police is I go to the same sort of forensic conferences that they would go to. So that's probably the main time where police, practicing forensic scientists and academics like me sort of inhabit the same space and really chat about what we do and the problems that we have, and talk about the good practices that we've come up with.
Oh, I would love to be a fly on the wall in those conversations. They must get really, really quirky and interesting fast. Well, Dr. G, or William, we're going to have to call it today, as we have gone over time, but I have really enjoyed interacting with you today and finding out about your lab and what goes on behind the scenes. And thank you to all our audience members and volunteers out there who have been asking their questions through. Now, Will, before I get you to let you disappear, if people want to find out more about yourself, oh no, have I just lost his signal again? Oh no. Well, this is awkward. Oh no, there he is.
You're back out. I'm back.
It was just at the moment that I was going to pass over to you to get you to promote yourself, or like, where do people find out about you if they want to know more, or even about your area of work?
Yeah, so I do have a Twitter handle. So at WJGEE is my Twitter handle. But honestly, probably the best one to go on is the university, or Griffith University's forensics Twitter handle, which I also spend a lot of time on, and that's at GU_forensics. And that is, you'll get more than just me on that one. So obviously you'll get my fingerprinting stuff, but we have anthropologists here who do a lot of, bone type stuff and bodies, and we have biologists who look at ancient DNA and studying the DNA in mummies and all kinds of really interesting stuff there as well.
Oh, now I'm curious and want to find out more. Well, thank you so much, Will, for joining us today. Now, for everyone else, before you disappear, just remember to check out our other live tours coming up later. Next week, we've got a session on Tuesday and Friday where we will be heading to a space science lab seeing satellites, and we'll also be touring a fertility and development laboratory on Friday. So keep an eye out for those 2 events that are coming up. Over the weekend, we do have Mug of Science episodes and podcasts being released daily, so please check it out. You might also find that if you go through our podcast playlist, you'll see one with William as well. So that's something worthwhile having a look at if you want to hear more about what he has to say. Now, if you've enjoyed today, I really want to strongly say that with Pint of Science being a registered not-for-profit organisation, we're run by volunteers, and we rely on this community to keep the science going. So your donation will enable future Pint of Science events to make science accessible to all. And if you're interested in donating, please visit our website, or there's this cheeky QR code, whoops, wrong direction. If you want to give that a quick little QR scan and send us a donation, that would be greatly appreciated. But if you're more into merch, this year's artist is Fijo, and his B artwork plays with the concept that there is no planet to be. Get it?